In the previous lecture, you learned how to use the photoresistor, and now we have a photoresistor on the breadboard connected to the Arduino on analog pin 0, and it's outputting values. Right now, these values on my bench are 9, 4, 8, and this is just an arbitrary value. I guess it doesn't mean much without converting it into something more useful. It's a value that represents the voltage on analog pin 0, and of course it varies depending on the ambient light that is hitting the photoresistor. But on itself, on its own, this number doesn't tell us anything about how much light there is in the environment. In this lecture, you will learn how to convert the sketch and potentially the circuit as well, so that the number that comes out relates to an actual illuminance value and unit. And there's a few out there, but the one that I have chosen for this example is lux. As you can see here in the Wikipedia article about lux, lux is the unit of illuminance or luminous flux per unit area in the International System of Units, and it's a meaningful number. So if we have a lux reading from our Arduino with a high value, we would be able to basically correlate this value or this number, this lux number, with an actual level of illuminance, and then we'll be able to make reasonable comparisons between lux readings and have an understanding of what that means in relation to illuminance. So let's have a look at how that would work. Right now, I'm just going to switch off the serial monitor. Right now, what's printed out by our Arduino sketch is just the raw value of the analog to digital converter. What we want to achieve is to have something like this, a simple linear formula that takes in the sensor value, that's the raw value that is coming out of analog read, and then transforms it into lux. Of course, the challenge here is to find out what these numbers in this linear equation should be. And there's a process to do that. So I've documented this process here, and essentially it has to do with first calculating an appropriate value fixed resistor for our voltage divider. In the previous lecture, I just picked 10 kilo ohm for the fixed resistor as a ballpark figure. But since we want more accuracy now, we're going to use this particular formula to give us this accuracy. This is called the Axel Benz formula. I'll explain how it works in a moment. So first, we are going to optimize our voltage divider circuit so that our readings from the photoresistor are more accurate, or as accurate as possible, as a first step. Then the second step, after we have optimized the circuit, is to find out what these two numbers will be in our linear equation. And the way to do that is to take samples of lux values using a lux meter, or in my case, I'm going to use an app on my phone. I'm going to use the app lux meter to get some representative values on my desk from different lighting conditions. And then we are going to also use the same conditions to take raw values from the photoresistor. This way we'll be able to correlate raw values with lux values, and then use these numbers to come up with the actual transformation linear equation that will take the raw number, convert it into a lux number. There's many ways by which you can do that, depends on how good you are in mathematics. A simple way that I have chosen for this particular lecture is to use an online calculator where you can plug in those numbers, and then the calculator will give you a line equation that connects those two coordinates in this case. We'll come back to this in a moment. So that's the process. So let's begin with step number 1, which is to measure the photoresistor resistance so that we can apply those numbers to the Axel Benz formula and come up with an accurate number for the fixed photoresistor. So the first thing to do here is to take some measurements of the photoresistor's resistance in different situations. And I've written down 3 situations here where I'll take measurements. So first one will be at night with lights off, then on my workbench with the lights on. So this would signify the two extremes, a lot of light, very little light, and then one in the middle where lights are off, but it's during the day and the windows and the shutters are open so that natural light is coming in. You can see the result of this experiment here, and these numbers are in kilo ohms. But I'm just going to take one quick measurement to show you how it's done. So here is my multimeter. I'm going to use the lux meter a little bit later. Talk more about that soon. I'm going to turn on the multimeter, reposition it here so you can take a better look of the result. So I have set my auto-ranging multimeter to the ohm meter function. Now to measure the resistance of the photoresistor, I need to remove it from the circuit, plug it into a different part of the breadboard. So this setting right now is the extreme number 3 with on my bench with all my lights turned on. So this would be the brightest setting for this area. So check the resistance now, and it is 0.83, let's say 0.83. What's the range here? Kilo ohms. You can see the range here. This again, 0.83. All right. I'll take this number and I will replace my previous measurement, 0.83. Like this. Okay, to save us a bit of time, I will accept the other two numbers for the two situations. This is darkness, and this is during the day with the windows open. So just save us a bit of time, I will keep those numbers going forward. So now I've got my photoresistor resistance measured in those different situations, and I will apply those numbers to the Axel Benz formula. In the Axel Benz formula, I multiply the minimum and the maximum measured resistances. In this case, it is the 0.83 and 90 figures. Multiply those, take the square root, and that's my fixed resistor value. Okay, so according to the formula, R1, the fixed resistor, is the square root of 90 times 0.83, and that comes to 8.64. All right, so this, of course, in kilo ohms, because that's what these numbers are. They are in kilo ohms. So I'm going to copy this number. An approximate value is okay, and replace my previous calculation with that. Done. All right, so step 1 is complete. This is my 8.64 kilo ohm resistor for the fixed resistor. So the resistor that I've got here is 10 kilo ohms. So I need to find a way to assemble a 8.64 kilo ohm resistance or close. And I think using the resistor pack that comes with the 3-in-1 kit from Sunfounder, I think I can put together one of those resistors. Is 5.1, let's say 5. Another one of the 2 kilo ohm resistors, and another one of the 1 kilo ohm resistors, and that will give me close to 8.64. It's probably going to be around 8.1 kilo ohms, but it's closer to the value that I need compared to the 10 kilo ohm resistor. So I'm going to unplug the power, remove the 10 kilo ohm fixed resistor, and then start assembling my new circuit. So let's go for the 5 kilo ohm resistor first. I'll go there. Then I'm going to go for another 2 kilo ohms. Of course, these are going in series. 2 kilo ohms plus a 1 kilo ohm. Like this. I'm going to move the sampling wire right there, the last pin of the last resistor in the series. And then ground will go to the other end of the series of resistors. And then I'm going to plug in my photoresistor right there, the end of the series. That's where power goes. So now I've got these three resistors that give me 8.1 kilo ohms. I could continue and go even closer to 8.6, but to keep this recording short, let's say that I'm happy with how close I am to the value that I calculated using the Axel Benz formula. So I'm going to apply power again. See the output in the serial monitor. Okay, and yep, it's looking good. And I can continue now with step 2 and measure the lux values. Now that we've optimized our circuit, let's continue and take a bunch of lux values and the output row values that are coming through here so that we can use them to create a linear equation like this one that converts the raw values into lux values. So the formula is going to look a little bit like this. Of course, the numbers are going to be different. All right, so let's do both at the same time, of course. You can see my final table that contains all of my measurements, resistance for the Axel Benz formula, the lux readings, and the raw value readings. And I'm going to take measurements just for 3 since my bench is already illuminated and I am now working in this situation where the brightness is at its fullest. To take the measurement for scenario 2, I would turn off all the lights, wait for a kind of sunny day, and then take a measurement there. Right now outside it's actually cloudy with rain about to start, so I won't be able to recreate this situation, but I've done this measurement at a time where the situation was actually possible. So I'm going to give you an example of how to take measurements in condition 3 and then use the values in this table to create the conversion equation. All right, so for that, I'm going to use my phone, and there's many applications that you can find that can do this. The one that I'm using is this one here. It's called Light Meter. Simply start it, and you can see that the application or the app will give you the lux reading for whatever you can see, in this case, inside this area of the frame that is getting from its camera. So right now, in condition 3, with all my lights on, the measured lux reading, I'm just going to move myself out of the way so I can get a clear picture, is 747, which actually is identical to what I have already recorded. All right. Now, the other thing that I need to get is the raw value that is coming out of the serial monitor, and that is 936. All right, so I'm going to change that to 936. Oops, try again. 936, and that would be the reading for the raw value. So I've got condition 3 with lux 747, raw value that is coming from the sketch from analog pin 0 is 936. And then for condition 2, where lights are off and the window shutters are open, lux is 70 and the raw value is 535. Or these are approximate numbers. So now I can go ahead and plug these numbers into this calculator to give me the linear equation that I need. So I need 2 points. Here's the first point, 535 and 70, which is already here. And here's a second point. Just now going to change this to 936 for the row value on the analog pin and 747 for the lux meeting from my application on my phone. Click on Go. And here is the formula that I need right here. And here is the equation. The next thing to do is to take this equation here and convert it into something that the Arduino Sketch can use. So I need to use decimals instead of fractions. Let's put it down there. Here's my calculator. The first fraction is 677 divided by 401, and that would be this much. And the second fraction is 334,125 divided by 401, and it is this much. All right, so you can see that the second one is a negative number, so this is 833.22. You can just go with the integer if you prefer. So one way to do this would be to go for something like this and not worry about the 2 decimals, and that would be enough. But the second one is important to include, say, a couple of decimal points. So that would be that. All right. So this is my new conversion formula. So let's upload it to the Arduino and see what comes out. So 737 versus 747. Yeah, as you can see right now, the Arduino is giving out a lux reading that is pretty close to what my lux meter on my phone is showing. So my lux meter 747, the Arduino 737. Obviously there's more optimizations that we can do here. My measurement for condition 2 was done when I was using the 10 kilo ohm resistor on my circuit. So I guess if I repeat the experiment now with this resistor configuration, then the sampled raw value for condition 2 would be more accurate, and that would give us a more accurate conversion formula. But for the purposes of this example, I'll accept the results that we're getting here as good enough. To conclude with this lecture, going forward and for the purposes of our Arduino Environment Monitor, I'm going to use this conversion formula to convert sensor values from the photoresistor into lux, and the resistor configuration that I've got on my breadboard right now. And I'm going to be using the same setup for my Arduino Environment Monitor. So put it aside and we'll be reusing it soon. Okay, let's continue to the next lecture now, where you learn how to take temperature and humidity readings with the DHT11 sensor.